0, 1 over g, 1 over g. Which is exactly the same thing that what we have over there. It's just written into a matrix. But it makes it a little bit clear now. Now, if we come back, if we come back to here, now you see that epsilon still the product of the properties of a matrix field with the properties of material times stress. And this matrix actually has a name. If you want to compute strains as a function of stresses, this one is called compliance matrix or compliance tensor. And what about if you wanted to compute stresses as a function of strains? What should you do if you want to compute stresses as a function of strains? Multiply everything by? No. It's a little bit more complex here. So when you're doing operations with matrices, it's not as simply as just divide something by that value. You need to multiply the inverse of that number. So if I multiply what is called the inverse of this times strain tensor, and I multiply to the left the inverse of this times d, this one is going to be an identity matrix because it's the definition of an inverse. And so from here, I'm going to get that sigma is going to be equal to this guy times epsilon, and that's actually goes by the name of C, and it's something which is called the stiffness matrix, which is the inverse of the compliance matrix. So yes, Mr.
If we had to do this,
A1.
If we had to do this, would we do this just like on MATLAB or something?
Would you like to do it on paper? No. To solve the inverse of this matrix?
Preferably not.
It's already, a lot of work to do the inverse manually with numbers. If you do it with just symbols and variables, it's going to take a lot of work. So if you don't trust what I say, go to Mathematica, to Wolfram Alpha, or to any other symbolical solver and take the inverse of this, and it's going to give you what I'm going to write right now. Okay? So I'm not going to ask you to do that. I'm just going to give you the result. It turns out that if you take the inverse of this matrix, then we can express the stresses as a function of strains and this is going to be equal to, I can do this. This is just a value that is going to multiply all the values inside the matrix. And still I'm going to have my 6 by 6 large matrix. And here I'm going to have the epsilon 1, 1, epsilon 2, 2, epsilon 3, 3. Epsilon, I always forget this. This is going to be 2 epsilon 1, 2. 2 epsilon 1, 3, and 2 epsilon 2, 3. And in here, the result of that inverse is that this is going to be 1 minus Poisson ratio, Poisson ratio, Poisson ratio, 1 minus Poisson ratio, Poisson ratio, 1 minus Poisson ratio, Poisson ratio, Poisson ratio, Poisson ratio. This is going to be all be zeros. Okay, I'm not going to write all those zeros, but it's going to be all zeros. This is going to be all zeros. And this is going to be 1 minus 2 times Poisson ratio. Just in the diagonal, Poisson ratio, 0, 0, 0, 0, 0, 0. Okay? So, now that we have this, we're going to see an application problem. Okay? So, I know that some of you are a little bit sleepy early in the morning. So, let's try to make an example over here. And that example is going to be an example directed to calculate horizontal stress. So imagine that you go close to the Gulf of Mexico, and you have Houston over here, and you have all the bayous and the rivers which are dropping sediments in the Gulf of Mexico. Why does the water in Galveston look kind of brown? It's because of the sediments, okay? It's because of the sediments, because of clay, silts. They are in suspension in the water, and that's why it looks like that. Because there are a lot of sediments coming from all over the rivers in the U.S. that are dropping sediments in there. So those sediments fall, and they create layers of sediments, right? And the more sediments you put, those just pile up on top. And if eventually, say that you had a block of sediment that had that shape at time 0 years, and that after 10 years it gets down here to the top, do you think it's going to have the same shape? It's going to conserve the same shape if it goes deeper and deeper and deeper and deeper. You remember what we talk about porosity as a function of effective vertical stress? Any suggestion? Porosity goes down. So the volume of this is going to stay the same or not? It's going to compress. And in which direction is it going to compress? In direction, let me be a little bit more specific here. Let's add the coordinate system, 1, 2, 3. In direction 3 only. And you know, I'm going to explain this in a bit, but just let me first draw this. Very likely, if you don't have any tectonic strains that push in this direction or that make the basin extend in this other direction, it's going to just very likely just compact in this direction. And why it doesn't expand? It doesn't expand because it's confined, right? Next to this amount of sediment, there is more sediment here to the side, more sediment here to the left. So if this one, you know, tries to expand to the sides, the one that's next to here and the one next to there too is also going to expand to the side because it's the same. It's undergoing the same process of compaction. If they all try to expand, no one is going to expand. So the strain in this direction is going to be 0. There's just going to be deformation in direction number 3, no deformation in direction number 1, no deformation in direction number 2. So if I want to convert this into some mathematical equations, I'm going to say that after 1 million years, epsilon 33 is a finite number different than 0, and epsilon 11 and epsilon 22 are equal to 0. Notice that also I haven't changed the shape of the square. So there are no shear strains either. So I'm going to write that epsilon 1,2 is equal to epsilon 1,3 equal to epsilon 2,3 also equal to 0. And now I want you to solve a problem. I'm going to give you 7 minutes for that. I want you, using this product, I want you to tell me, first of all, what is going to be sigma 3,3 as a function of epsilon 3,3, and I want you to tell me what is going to be sigma 1,1 as a function of sigma 3,3. Forget about pore pressure for the moment. These are all effective stresses, so that's everything you have to know. Okay, so let me. I cannot zoom out anymore, but this is what I want. Okay, I want sigma 3,3 as a function of epsilon 3,3. I want sigma 1,1 as a function of sigma 3,3. Okay, can you work through those equations? First 3 people, I give them extra points, class participation points. Okay? You know what to do, Mr. Barmal? Yes. Which one? This one? Okay, you already have the matrix, okay? So if you need a matrix, just let me know. And I'm going to write it here just in case. Yes, Mr. A1.
This should be a function of like if sigma 3,3 is supposed to be a function of epsilon 3,3, does it only have to be epsilon 3,3 or can it have like some other values as well?
No, it just can have just sigma 3,3. You will see that some things are going to simplify in there, and then you're just going to have this as a function of sigma 3,3. Anyone got the answer? Yes? Yes. Mr. Lau, what did you get?
For sigma 3,3,
Yes.
I got 1 minus cosine ratio times 3,3
Okay.
times E
Okay.
divided by 1 plus cosine ratio times 1 plus 2 times cosine.
Okay, you guys get all the same result? So how do you get that one?
I just like multiplied the distance.
Yeah. So this one, look, this one is going to go, where is it? Here is it. This one, we say in our problem, this one is going to be 0, 0, and this one is going to be 0, 0, 0. So when you calculate sigma 33, which is the one over there, you multiply all of these times this one plus that one is going to be what? 0, right? This one, well, sorry, we're looking at sigma 33, so this is that row that we have to look at. This one plus that one is going to be 0. Poisson ratio times 0 is 0. The only one that survives is this one. 1 minus Poisson ratio times all of that times sigma 33, which is this thing over here. Okay? Okay, so someone else other than the middle Dawes, tell me what is going to be sigma 11 and sigma 22.
It's going to be E times Poisson ratio times epsilon 33.
Okay, so let's do the multiplication, for example, of sigma 11. Say again, what's going to be?
So it's E as in Young's modulus
Yeah.
times Poisson ratio times epsilon 33 divided by the same thing right there. 1 plus Poisson's ratio times 1 plus 2 times Poisson's ratio.
I think we can simplify that a little bit. Did someone else get another answer? No? What about you guys in the back? No? You got an answer? No? Okay, I'll let you work a little bit more on that, okay? In the meantime, I'll work here in those same equations. I'm just trying to explain what I see in the matrix as an equation, okay? So if you get the answer, tell me, okay? I'm just developing here a solution for everyone. But if you got it faster than I do, just jump in.
I think I have it.
Okay, tell me.
E over 4 plus 2b squared times.
No. Anyone else? No, but you cannot participate anymore. Anyone else? Miss Kale, you have the answer? No?
From what you're doing, I'm guessing not.
So everything, I'm just writing up what I have over there. Okay, did you get there, guys? No? So look what I did. Sigma 11 is, this is 0 times 1 minus Poisson ratio times 0 is 0. Poisson ratio times 0 is 0. We just get Poisson ratio times all of this times epsilon 33. So all of that times Poisson ratio epsilon 33. But you know what epsilon 33 is from the equation above, right? So epsilon 33 is this times that divided this. So sigma 33 times the denominator over there divided that. And from here, you see E E 1 minus plus 1 minus plus Poisson ratio times that, and the result is that sigma 1, and also I can expand this for sigma 2 because it's exactly the same thing. It's Poisson ratio divided 1 minus Poisson ratio times sigma 3. And that's it. So let me write that over here. So we said that epsilon 3, sigma 3 is going to be 1 minus Poisson ratio Young modulus divided 1 plus Poisson ratio 1 plus 2 Poisson ratio, and this is just going to be simply 1 minus Poisson ratio 1 minus Poisson ratio. And this is a very important finding. Yes, Mr.
I just had a question
A1,
about
yes.
how we got the constant of Young's modulus divided by 1 plus Poisson's ratio, the one that's like right before the 6 by 6 matrix, like on the top page. Yeah, the one that we're like multiplying with.
This one?
No, that one over there.
That one?
On the left. Yeah, that one.
Well, no, I'm just taking the inverse of this matrix over here, of that one. You take the inverse of that one with Mathematica, knowing that G is, where is G? The G is that, and you're gonna get that result. I'm not proving here how I got this one, but I'm just asking you to believe me. And if you don't, G is the shear modulus. This is called the shear modulus. Which, I repeat again, for linear elasticity, notice that we just have two independent coefficients. And let me emphasize that here. Okay. Yes, you have a question, Ms. Kale.
Just a question. How do we know off the bat that sigma 2 is equal to sigma 1, 1? Did we do it manually by hand, or like did we have a?
No, I just solved for sigma 1, 1, but it's exactly the same procedure for sigma 2, 2 because they are the same equations.
Oh, just math, not like
Yeah.
pre-constructed.
Yeah, it's just math,
Okay.
and it's applying the same procedure. Okay, so two main takeaway messages from this simple problem. The first one is that do you remember how we used to talk about in 1D Hooke's law? Let me bring it right next to this one. That stress is proportional to strain through the Young modulus. Well, here stress in the same direction is not proportional to the Young modulus, it's proportional to something else. When you have a confined solid that cannot expand to the sides, the proportionality factor is not anymore the Young modulus because this is confined, it's not unconfined. And this is the case in the subsurface, so it's not the same. Young modulus is not enough to characterize this relationship. And actually this guy has its own name, and it's called the constraint modulus, and it goes by letter M. All of this. Second thing, you have a question? I thought you had a question. Okay. The second thing is that now we can calculate what is the horizontal stress as a function of vertical stress. And if you remember, this is the relationship that Ms. Soldawi pointed out before, that you learned about how to calculate horizontal stress. is not wrong, but it involves this very important assumption of no tectonic strains from the sides. And also involves assumption of linear elasticity, which many times those two are not fully accurate to describe the state of stress in rocks in the subsurface. This is an approximation, and many times it works reasonably well, but many others it will not. Okay, but it's very useful, and actually, we tend to use it a lot because under these conditions, it will give you a reasonable result. Okay, so how are we doing with time? We have 15 minutes. So let me see. Let's talk about an application problem, and this is what you have to do in your homework as well. Let's talk about a procedure to determine horizontal stress, and I mean total horizontal stress, or both, with linear elasticity. Who is your best friend in geomechanics? You remember that? I told you who should be your best friend. No? Anyone? No, I'm not your best friend. Jeffrey could be your best friend. Your best friend is total vertical stress. Okay? So number one, I give you data set, anything. Okay, this is going to be a general procedure. Number one, well, actually, let me do a little diagram there to exemplify this a little bit more. You're drilling, conserve probably about wellbore stability at some location at depth Z. And here you have water, and let's say there is a connected path of water through that point. Number one, you determine total vertical stress. That's your best friend, okay? And remember that we're going here, okay? We're going to determine horizontal stress. You already know how to do this. Number two, what do you do? Well, what you have done so far. You will determine pore pressure, okay? And this may not be super simple sometimes. Sometimes could be hydrostatic, and that's very simple to do. Some other times it may be non-hydrostatic. And if it's not hydrostatic, probably in that case, I'm going to give you ahead the overpressure parameter value, or you will have to work through the equations in which porosity it takes the shape of something like this. And there it should be sigma B. But you're going to have pore pressure, okay? You're going to either you can calculate it, or I'm going to give the value to you. Third, what do you do after that? Now, look, now you can determine sigma B, which is equal to SV minus P. You know that as function of depth everywhere. And only after you have calculated the effective vertical stress, you're going to be able to calculate the effective horizontal stress. In this case, this is going to be just a simplification, okay? We're going to see that this equation gets a little bit more complicated later on, but it's what we have just proved before with that equation over there. Sigma h is going to be Poisson ratio divided 1 minus Poisson ratio sigma v, and remember, this is a simplification. I'm gonna give you the full equation later on, but the procedure is the same. And only after that you can calculate the horizontal stress, which is going to be sigma h that you just calculated plus something that you already know, you already knew, which is the pore pressure. This is the final answer. So if you apply that workflow, then you're not going to make any mistake in computing the total horizontal stress. Yes, Ms. Aldawi. Well, I didn't want to go into details because we're going to see later a minimum and a maximum. Let's just call it horizontal stress, and it's the same in the two directions, so there is no minimum or maximum. They are just the same. All right. So before you leave, I'd like to talk about this very important parameter now that turns out to be the Poisson ratio. Okay, a parameter probably not that you didn't pay a lot of attention before, but now it becomes a very important parameter. So let's try to see what that value is. What is the range of Poisson ratio, possible range of Poisson ratio that we discussed before? And this is an exam question, guys. I really want you to know what the Poisson ratio is. 0 to 0.5. As a result of that, this guy over here, which is called the lateral stress coefficient, we're going to calculate its value. If the Poisson ratio is equal to 0, what is going to be the value of this guy? 0, right? And let's try to understand what's going on here. That means that if you had a solid to which you apply a stress in one direction, it does not deform in the direction perpendicular to it, because the Poisson ratio is equal to 0, right? And if that's the case,